Alright, thanks for watching, and today I would like to tell you why symmetric matrices are so awesome. So consider, for example, this matrix A. It is symmetric because literally it's symmetric along its main diagonal. And the main definition is that simply A transpose equals A. And why are symmetric matrices so cool? First of all, not only that their eigenvalues are always real, so we never have to deal with complex eigenvalues, but also we can super diagonalize a matrix. So do something more than diagonalization. And in fact, let's do that today. So let's find D diagonal and P. So usually invertible, but now it's super invertible, so orthogonal. And orthogonal just means the columns of P are orthonormal. So the dot products of different vectors are 0, and each vector has length 1. So it's like even better than invertible, such that usually in the diagonalization process we have A is PDP inverse, but here's the nice thing. If P is orthogonal, it actually means that P inverse is P transpose. So instead of having A be PDP inverse, we can do something even easier or more powerful. A is PDP transpose. And no, not like Peyam Tabrizian, P transpose, just that. And this is super useful because it allows us to decompose A in an easier way. And also there's another video on quadratic forms that shows you why having A be PDP transpose is more useful than having A as PDP inverse. All right. And how do you do this? And I like to call this the ultimate linear algebra problem because it actually combines diagonalization with the Gramschmidt process. So the first thing is find the eigenvalues of A. So find eigenvalues. And so, you really find determinant of lambda I minus A. And lambda I minus A is lambda minus 3, 2, 4, minus 4. And then 2, lambda minus 6, minus 2, minus 4, minus 2, lambda minus 3. And I will not do the details because you'll see otherwise the video is an hour long. But if you find the eigenvalues, so if you find the determinant of this and you set it equal to 0 and you solve the equation, you'll basically get lambda is minus 2 and lambda is 7. So that's that. And then next, let's find the eigenvectors. And again, this part I will sort of skip as well. So you would do null space of minus 2i minus A. So you would plug in minus 2 in there, and you would get basically, I think, the null space of minus 5, 2, minus 4, 2, minus 8, minus 2, and minus 4, minus 2, minus 5. If you do that, if you reduce and you find a null space, turns out you get that the span is 2, 1, minus 2. So that is one eigenvector corresponding to minus 2. Next thing, let's do null space of 7i minus A. Well, here it's a null space of 4, 2, again 42, minus 2, 2, 1, minus 2, minus 4, minus 2, 4. And notice what's nice, all the rows are sort of multiples of each other. So really, it's just a null space of 2, 1, minus 2, 0, 0, 0, 0, 0, 0. And again, if you find a null space, you should get the span of 1, 0, 1. and 1 minus 2, 0. So that's the usual diagonalization process. So D would be the matrix with minus 2, 7, 7, and P, usually the matrix with 1 minus 2, 1, 0, 1, and 1 minus 2, 0. And then you would get A is PDP inverse. But what we would like to do now, we would like to super diagonalize a matrix. So we would like to find A equals to PDP transpose. And in particular, and I'll explain this after I do this, what we would like to do, to each eigenspace, you want to apply the Gram-Schmidt process. In other words, you would like to find an orthonormal basis for each eigenspace. Okay. And again, very important, you don't do Gram-Schmidt to all the 3 vectors, you do it to each space separately. So let's do that, and I think this one I'll do in more detail. So that's why it's a beautiful problem. So it's great problems for final exams and stuff, if you like, because it combines diagonalization and orthonormality and stuff. So step 3, so apply Gram-Schmidt, not Granny Smith, but Gram-Schmidt to each eigenspace. Again, don't do it to all 3 vectors. It's a waste of time. And basically what we'll get, instead of having a long Gram-Schmidt process, we essentially have 2 very short Gram-Schmidt processes. So, first of all, consider the eigenspace corresponding to minus 2. So I write it as E of minus 2. And remember, it's just the span of 2, 1, minus 2. So U would be your vector 2, 1, minus 2. And remember, for Gram-Schmidt, if you just have one vector, then you basically just get that one vector. So that would be an orthogonal basis to your eigenspace. And to get an orthonormal basis, you take this vector, 2, 1, minus 2, and you divide it by the length. The length of that vector, it's square root of 2 squared plus 1 squared plus minus 2 squared. And that turns out to be actually square root of 9, which is 3. So W is 1/3 times that, which is 2/3, 1/3 minus 2/3. Actually, quite nice, And then you're done with this eigenspace. So you see, usually instead of having a huge Gram-Schmidt process, you have 2 very simple ones. Now, let's do the other one, which is a bit more complicated. So E7, which is the span of 1, 0, 1, and I think 1 minus 2, 0. Okay, then what it's saying is, well, your first vector is 1, 0, 1, and your second vector is 1 minus 2, 0. And then, how do you do Gram-Schmidt? Well, first of all, V1, sort of the first vector of your orthogonal basis, will just be U1, which is 1, 0, 1. And remember, just not to confuse yourselves, once you use this vector, you just cross it out from your list, just so that you're not tempted to use that vector again. Now, how do you find your second vector? It's using orthogonal projections. So the picture is as follows. And again, I'd like to remind you, there is a video on the Gram-Schmidt process if you're confused about those steps. So, then what do? So you have your vector V1 already. And you have this other vector you haven't used, U2, which is 1 minus 2, 0. Okay. And V1 is, again, 1, 0, 1. And maybe let me draw it here, so this is more suggestive. So this is V1, and this is U2. That's V1, which is 1, 0, 1. U2, which is 1 minus 2, 0. And the point is V1, it spans a line. And what would you like to find is simply what I call U2 hat, which is just the orthogonal projection of U2 on this line V1. And there is a formula for that, luckily. So how do you find it? Oh, much better. So U2 hat, first of all, it's in the line generated by V1. So it is a multiple of V1. And the way you do this, you take U2, you hug it with V1. So U2 dot V1. And then V1 is so happy it hugs itself. So V1 dotted with V1. And in other words, this becomes 1 minus 2, 0 dotted with 1, 0, 1 over 1 minus 2, 0, sorry, 1, 0, 1 dotted with 1, 0, 1 times 1, 0, 1. And if you do this, you just get 1 half times 1, 0, 1. And that's 1 half, 0, 1 half. Careful, do not rescale that vector. That would be wrong. And then, what is a vector V2? It's simply a vector that's perpendicular to V1, which in this case, it's U2 minus U2 hat. So that's V2. So you see, that's why the Gram-Schmidt process produces, an orthogonal basis. So V2, it's U2 minus U2 hat. And in this case, 1 minus 2, 0, minus 1 half, 0, 1 half. And that becomes 1 half minus 2 minus 1 half. And this one, now you're allowed to rescale it, because any multiple of this vector will still be perpendicular to V1. So just rescale it to 1 minus 4 minus 1. Okay, that's good. We found our V1, 1, 0, 1, and we found our V2, which is 1 minus 4 minus 1. And indeed, you can check that if you dot those two vectors, you do get 0. So this gives us an orthogonal basis to our eigenspace. And now, if you want just an orthonormal basis, you just divide each vector by its length. So let's see, so what did we get? We got that V1 was 1, 0, 1, and V2 was 1 minus 4 minus 1, and so W1 is just this vector divided by its length, which is 1 over square root of 2, 1, 0, 1, and W2, it's, I think, 1 over square root of 18 of 1 minus 4 minus 1. Okay, and let's see. And that's your answer. So basically, 1 over square root of 2, 0, 1 over square root of 2. And then this is just, I know it is 3 over square root of 2. So, but let's just leave it like that. 1 over square root of 18 minus 4 over square root of 18 and minus 1 over square root of 18. Okay, wonderful. So we do get an orthonormal basis for our second eigenspace. And then the question is, what is the answer? It's interesting. The question is, what is the answer? Where the answer is simply D is minus 2, 0, 0, 0, 7, 0, 0, 0, 7. Okay. And then P, it's simply the matrix of your normalized eigenvectors, so 2/3, 1/3, minus 2/3, and 1 over square root of 2, 0, 1 over square root of 2, and 1 over square root of 18, minus 4 over square root of 18, and minus 1 over square root of 18. And notice, if you check this, indeed, the columns of P have length 1, and moreover, they're perpendicular to each other. So indeed, P is a matrix whose columns are orthonormal, and that's just the definition of an orthogonal matrix. So indeed, P is orthogonal. How beautiful is that? All right, and just so this was how to do the problem, just a little discussion. So why does that work? It's the beauty of symmetric matrices. And also, why do we have to do Gramschmidt and everything? So, here is the most important fact about symmetric matrices. Namely, if A is symmetric, so if A transpose equals A, and you have two different eigenvalues, then if you take an eigenvector corresponding to lambda 1, let's call it V1, and an eigenvector corresponding to lambda 2, which is V2, those two things are automatically perpendicular. In other words, eigenvectors corresponding to different eigenspaces are automatically orthogonal. And the reason for this is, it's kind of neat. So consider AV1 dotted with V2. On the one hand, it's lambda 1 V1 dotted with V2. Because AV1 is lambda 1 V1. On the other hand, there's this property of dot products that says this is just V1 times A transpose V2. But A is symmetric, so this is just V1 times A V2. And that's just V1 dotted with lambda 2 V2. And that's lambda 2 V1 dotted with V2. And so, lambda 1 times V1 dotted with V2 is lambda 2 times V1 dotted with V2. But because both of them are not equal, so they're all different, this means that V1 dotted with V2 has to be 0. And therefore, we get that eigenvectors corresponding to different eigenspaces are automatically perpendicular. In particular, in this example, we had, our space E7 and our space E2, E minus 2. And basically what this is saying, those spaces are perpendicular. If you take an eigenvector here and an eigenvector here, automatically they're perpendicular. But why did we use Gram-Schmidt? Because among each eigenspace, the vectors are not necessarily perpendicular. And therefore, after using Gram-Schmidt, you know that those two vectors are perpendicular by Gram-Schmidt. You know this vector is perpendicular by Gram-Schmidt. But by that other fact, we know that if we take two vectors here in different eigenspaces, they will also be perpendicular. So, therefore, the columns of P now, by construction, will be perpendicular. And by normalization, they'll have length 1, so the columns will be orthonormal. So this is really, really cool. And that's why this works. And just in case you're curious about further topics, there is this beautiful theorem called the Spectral Theorem. And, okay, I have to say, Spectral Theorem, the name sounds amazing. The result is okay. I feel it shouldn't deserve the name Spectral Theorem because that's just such a beautiful word. But anyway, so what does the Spectral Theorem say? It says this is true. Namely, if a matrix is symmetric, then if A is symmetric, that's the same thing as saying A is orthogonally diagonalizable. A is PDP transpose. In fact, we have shown this direction, and well, this direction is not hard, just compute A transpose and see that it's just A. But what's nice about this not only works for matrices, it also works for more general linear transformations on infinite dimensional spaces. And right now I forgot what the analog of symmetric is, but it's really, really cool. Probably Hermitian and something, I think, about compactness of the spectrum or something. But this is really cool. And lastly, there is something called the spectral decomposition, which is a neat way of decomposing a matrix into sort of one-dimensional projections. Here's what I mean. If A is PDP transpose, then let P again be the eigenvector, so UVW. And this is the eigenvalues, let's say lambda 1, lambda 2, lambda 3. And then P transpose is just UV and W as rows. Then what does a diagonal matrix do? It just multiplies each row by the value. So this is UVW times lambda 1 U, lambda 2 V, lambda 3 W. And it turns out if you multiply those matrices together, you will indeed get lambda 1 times U transpose U plus lambda 2 V transpose V, UU transpose, the opposite. UU transpose VV transpose plus lambda 3 W transpose. And this is what's called the spectral decomposition of symmetric matrix A. And let me quickly mention what this is. So there's another video that I've done on what does a rank 1 matrix look like. In particular, a rank 1 matrix looks like the form UV transpose for some vectors U and V. So those things, they're really rank 1 matrices. And basically what you're doing, you're decomposing your matrix A into what are called one-dimensional subspaces. Because the rank is the dimension of the column space, which tells us those matrices have column space that are one-dimensional. So really you're projecting your matrix on a line. And for example, what you're doing, if you have the space, span of 2, 1, minus 2, you're literally taking a vector x and projecting it on that span of 2, 1, minus 2. So in other words, what you're doing, you're taking your matrix A and you're projecting it on just the eigenspaces of A. And that sort of makes sense if you think about it, because what happens if you do UU transpose on X? Well, this is just like a dot product. So this is like U times U dotted with X, and you can just think of it as X dot U times U. But if U is orthonormal, then it's just U dot U is 1. So X dot U dotted over U dot U times U. So really what those are is just you projecting X on each eigenspace. So think of like one eigenspace being here and then another eigenspace being here. Then basically what this does, it takes X as an input and decomposes it as 3 one-dimensional projections. So for example, what does one of those projection matrices look like? Well, remember we had this eigenvalue minus 2, and we get the other eigenvector, 2/3, 1/3, minus 2/3, times 2/3, 1/3, minus 2/3. And if you actually do this, you get actually a 3 by 3 matrix. So it's a 3 by 3 matrix, but not with lots of info. It's just, in this case, minus 2 times 4 ninths, 2 ninths, minus 4 ninths, and 2 ninths, 1 ninth, 1 ninth, and minus 4 ninths, minus 2 ninths, and minus 4 ninths. And you can do this with all the other eigenvectors, and if you sum them up, you should get the matrix A. So it's a nice decomposition of a symmetric matrix, I think. All right, and that's all you need to know about symmetric matrices. I hope you enjoyed this, and if you want to see more math, please make sure to subscribe to my channel. Thank you very much.